Yes, take attendance.
I want my pants. My dad's looking through What? Oh. Why did you?
Why did you this is my shirt. This is casual. This is my uniform. This is my formal clothing.
Not casual.
My water.
Hey guys, let's start.
You should join the basking.
Okay, so we're done with the alternating current. So we try to do some questions about it, the magnetic. Okay, so what do you learn about alternating current? First is, what is RMS value? 2 marks. What is RMS value? A value of a AC current equivalent to a DC current that dissipates
energy.
the same heat energy or rate of heat energy. Rate of heat energy across the resistance. Okay, across the resistance. RMS value. Okay, a value that is equivalent to a DC current. Yeah. So that's the highlight of this topic. So IRMS is I naught over root 2, VRMS, V naught over root 2. Okay, so for a sinusoidal. Yeah, for a sinusoidal wave. For any other shape, square wave, you square the graph, in the graph, and I told you what to do, right? Okay, then rectification towards the end. Last class we did that. So we use a diode, then we use a capacitor as to smoothing the what do you call the output. Okay. Okay, so let's go some passes today. So we go to the exam here. Topical. Bridge physics. Paper 4. Go for the alternative current. Okay, so recall back. How are you going to do these questions? Just get first question. Okay, so what's the answer for the name? Suggest what advantage of full wave rectification as compared with half wave rectification. What is the advantage of full wave compared to half wave?
More consistent voltage.
More consistent voltage, therefore more power available for the load. So more power is available for the load because consistent voltage. So actually more power available because half wave rectification, first half supply power, second half no power for the load, and again you have power. So full wave, it gives more power to the load. More power. It will be more power to the load. So full wave contributes more power compared to the half wave to the load. You will see that notes. Okay. B, so full wave circuit, the diode. Okay, read the question. The rectifications produced using a circuit. So all diodes are maybe considered to be ideal. Ideal diode means zero resistance. Okay, where is the time of the alternating voltage applied? See, so you have from the power supply. Sorry, the one what? The variation with the time t of the alternating voltage applied to the circuit is shown in the figure 7.2 and 7.3. Okay, so two graph. So on the axis of 7.2, draw a graph to show the variation with time t of the potential difference across diode A and 7.3 for diode B. Let's pull up. They want you to sketch the voltage versus time graph for diode A and diode B. So diode A is where? Diode A is on top. For diode A, how the voltage variation going to be? And the A obtain the voltage. Okay, so how to do this? When I need to show you. And let's say the upper terminal is positive. We go for A first. You want to drop B versus T graph of A. You know the power supply here is alternating up and down. Completely. But when up is positive, how the voltage will change for A? When up is positive, that means upper cycle, positive cycle. So the A going to use any voltage? A going to be forward bias or reverse bias? When up is positive. When up is positive, A is going to be forward bias or reverse bias? Forward bias. So when diode is forward bias, is it uses any voltage? No. Why? Low resistance. Low resistance. So for the first half cycle, the voltage across A is 0. It never consumes any voltage. Current is flowing through A, but it never consumes any voltage. So A must have 0 voltage. For the first half cycle. Then second half cycle, when down is positive. When down is positive, is there any A current flow through A? Yes. No current flow through A, right? When down is positive. Come through.
So I. Oh, no, I think it's so.
Current flow through A. So A have like a high potential, safety high potential. Okay. So how the graph will look like? So I go to the whiteboard. I cannot write this. So how the graph will look like? So the first cycle, no voltage. Okay, then you have a voltage for the A, then no voltage for the A. This for the A. Yeah. It doesn't consume voltage, then it consumes voltage. Yeah. This voltage is for voltage across the what do you call? Across the load. Yeah. So it's always positive. Then next we go for the B. B will be the other way around, right? B, the first cycle, B will have voltage. For the case of B, of course. For the case of B, the B case have to be here. So here, then here 0. Here, that would be. Okay. This is for the B. Negative. Yeah, okay. But make it positive. But it should be one side. Yeah, okay. But they have to must have a phase difference of how much? 180. 180 of phase difference. Okay, so yeah. So diode take turn. When current flows to the diode, it never use any voltage. The other voltage, other diode takes voltage. So they actually peak at a different phase, okay, different time. Okay, so that's the first one. So drawing 1 and 2. Okay, see, draw a symbol for a capacitor, connect into the circuit so as to provide smoothing, because this is just connect a capacitor parallel to the load, right? Connect a capacitor parallel to the load. So easy mark. Okay. So then C2, show the variation with time t, the smoothing potential difference across the resistor R. So how the smoothing happens? Show the variation with time t with 7.1. Let's say 7.1. Where's the 7.1? This one. Oh yeah. So for the resistor R, yeah, show 7.4. Show the variation of T, the smooth potential difference. Show the variation of the T for the smooth potential difference across the resistor R. Yeah. State how the amount of smoothing may be increased. One mark. Or increase the capacitance. What's the reasoning you can tell? Let's say it's a 2 marks question. Why increasing capacitance? It's better smoothing. So how are you going to explain? Based on what formula you can explain? C equals to changes of Q over changes of V. So changes of V is changes of Q over C. Right, make it rearranging. So the capacitance is inversely proportional to the change in the voltage change in the capacitor. Voltage, if the capacitor voltage drop by 1 volt means the load voltage is going to drop by 1 volt because they are parallel. So the voltage drop in the capacitor is dependent on the capacitance of the capacitor. They are inversely proportional. This big capacitor means the voltage drop across the capacitor is going to be small. Therefore, the voltage drop in the load will be small. So the ripple, better smoothing, the ripple is smaller. The changes of V is actually in this diagram, which is your changes of V from the peak to the bottom here. This height is the changes of V, right? So the changes of V become smaller. So here you have the ripple like this. So let's say you have a graph like this. So this height is your changes of V. So how do you reduce it to become more flatter? So use big capacitance. Okay. So 1 mark state big capacitance. 2 marks explain. So changes of V equals to changes of Q over C. So capacitance voltage drop. So big capacitance. Okay. Explanation. Okay. So we got the idea. Okay, that's the first question. This is the mark scheme. So hope this reminds so more output power, less ripple, smoothing capacitor for using the full wave. Full wave, I think more output power. So showing out the rectification, similarly for unregistered for A and B. By the capacitor. Okay, so one example. Yeah.
For the first part, right? For the first key, whether we drop last drop voltage.
For C1.
Sorry.
For C1.
C2.
C2. Yeah.
For the first thing, then the lesser ripple.
This is with capacitor, right?
Yeah.
Okay. So now what's your question?
Before the first key, will there be a drop in? But will there be less ripple also? Because the capacitor is like still charging, right?
Capacitor is still charging, okay. But
Before this, it's like a hump now, right?
yeah, like how it becomes 0, right?
Yeah.
So the capacitor has charged right from the arm. So it charges here. Yeah. Okay. So only between the first and the second hump, then there will be less ripple. Right? Before the first hump, will have less ripple. The first one no change. Yeah. Here no change. Before that, nothing at all. Before that, yeah. Here you will have. When it's charging here, okay. Before that, no. Here. Yeah. Okay, the important is, of course, ripple depth, right? We need to reduce it, reduce the capacitance. So here is charging here. It's charging here. Here charging. In this case, here charging. So
Why do you need big capacitors for?
why data?
For this moving? Why do you need big capacitors?
You need capacitance with a big value. Because just now I told you, if big capacitance means the potential difference will be small. I mean the C equals to QOV, right? Yeah. QOV. So big capacitance means the same amount of charge released, the amount of voltage drop in the capacitor will be very small. It's a very big reservoir, So it releases, let's say, at the beginning you use a small reservoir, small capacitance. So let's say you release 2 coulomb charge. Let's say voltage drop the capacitor 2 volt. 2 coulomb charge, 2 volt will drop. Small reservoir. Now you replace with the big capacitor, big reservoir. 2 coulomb charge release, the voltage drop will be very small. So the ripple will become small. So to be easier, you just take the capacitance is inversely proportional to the voltage drop, the changes in the voltage. Okay, so less ripple. Okay, so let's see more questions. So yeah, so another circuit. So the things there. So 2 marks, draw symbols for the 4 diodes and produce polarity across the load as shown. So how you draw? So you choose the load junction. So load junction is at the side. So from either here or here, from here maybe. So out like that. So, okay. Yeah, so here the from the left corner the arrow is moving upwards, upwards and join back down. Okay, going down. Okay, next 3 marks. Oh, this is removed from the syllabus. Transformer not anymore in your syllabus. So we skip this. Okay. Transformer was last time learned VP, OVS, NP, ONS, right? Now from A level they remove it. But indirectly you need to know transformer in which topic? In your induction, electromagnetic induction. And AC also linked to transformer, but the formulas has been removed, so we won't be going that way. Okay, so very famous terms they will ask always. What is meant by root mean square value? A value of a AC current that equivalent to a DC current that dissipate the same rate of heat across a resistor. Okay, don't say heat, rate of heat. Okay. So a value of AC current that equivalent to a DC current that dissipate the same rate of heat across a resistor. Okay, RMS value. Okay, come on guys, very fast. Let me answer. So this is your AC voltage formula frequency. What is the peak RMS frequency? So peak is of course how much? 220, right? 220. RMS voltage 220 divided by root 2, right? 220 divided by root 2 gives you RMS. Frequency is how? 120 pi is your omega, right? 120 pi is your omega. 120 pi equals to how much? 2 pi f, right? Omega is 2 pi f. So 120 pi equals to 2 pi f. So f is how much? 60. Frequency of 60, right? Okay, let me add another one. Never asked. What is the mean voltage? Say the fourth one I have. Mean voltage. How much? mean voltage. RMS voltage peak over mean voltage, mean current, same as mean current, mean voltage. What do you do? You take the area of a period, right? Area of a period equals to the I mean times period, right? Teach you last class. So the area within the period, half of the period is up, another half is at the bottom, right? So total area is how much? 0, right? So mean voltage? 0. Okay. So the area on top and bottom is the same. Mean value becomes 0. Okay. So mean voltage 0. The area up and down is not same. Then mean value will have some value. Will have value. Okay. Come on. Okay, come on. This needs to be calculated. Can you calculate for me? Give a try. Alternating voltage to apply across the resistor such that the mean power. You have to be careful when to use RMS, when to use peak. So the mean power is 1.5 kilowatts. Calculate the resistance of the resistor. Go back to the equation. The mean power is 1.5 kilowatts. Calculate the resistance of the resistor. Okay, hope you remember the mean power, 1.5 kilowatt. Scroll up. Mean power, calculate the resistance of that. Okay. Mean power 1.5 kilowatt, calculate the resistance. So, what formula do you use? You want the resistance. So, which formula is best? Power equals to, three formulas, IV, I squared R, V squared R, which is more suitable here? V squared over R. And so V, you know the V, so they ask you for R, suitable is V squared over R, right? So P equals to V squared over R. Okay, last time, finding equation is one problem, we got it. But now, AC, another problem, what V to use? VRMS, VP. Use PP or VRMS for this case. The power is, we will use substitute as 1.5, power 1500. And 1500 equals to V squared over R, which we use? RMS. Use RMS value because it's average power. Average power, VRMS. They just say power, VRMS. If they say peak power, and then VP.
So why don't you use the mean voltage?
Mean voltage. Why we can't use mean voltage here? Why we can't use mean voltage? Because which value is equivalent to the direct current value? Which value of the AC is equivalent to the direct current value? Give the same power dissipation. RMS value. So you have to use RMS. Okay, not the mean value. Okay, that's why at the beginning of the topic they highlight which is the equivalent value, RMS. Okay. So because the power formula I squared R V IV originated from DC, right? DC. So AC is another planet. Now we found that which value equivalent to this is RMS value. So you have to use RMS. So here you have to use RMS. V squared over R, and V must be the RMS value. So what's the RMS value here? 220 divided by √2, and you get RMS value. Okay. So hope the idea you might have. Those who think of V squared over R, good. Those thought of V must be RMS. Okay, so that should be the working one, right? So V squared RMS should be the RMS value. Okay, so it's 16. Yeah, right? Okay, so another one. Same question. Different variant, same question. Okay. Another question. So IT alternating current, direction current with the time sinusoidal. Explain why, although the current is not in one direction only, power is converted in the resistor. 2 more. Variation in the current with time is sinusoidal. Current is flowing back and forth. Now change direction, passes the resistor. But the power is converted in the resistor. Explain, although the current is not in one direction, power is still converted to the resistor. Okay, why? Okay. Whether current flowing to the right or current flowing to the left, power still transferred to the load. Maybe a light bulb. The light bulb always light up, whether the current flowing to the right or to the left. The light bulb always light up. You get the power. Why? Because power is a scalar one. It's not affected by the direction of the current flow. Okay? The power is a scalar quantity. It doesn't affected by the direction of the current flow. Okay? So therefore, you always get power regardless of which direction current is flowing. The carrier is the charge. The charge carries some energy to the load. Which direction the load, the charge go transfer that energy, it doesn't matter. As long as the energy has been supplied to the load. So who's the transporter is the electron, right? The electron travel which direction doesn't matter. But as long as transfer the energy. Okay? So yeah, the first you can say this power is a scalar quantity. It's a scalar quantity, so it's not affected by the direction of the current flow. Okay? So therefore, power still transferred. Okay? Okay. Now, question? Leave the relation between root mean square current and peak current reduce the value of average power converted in the resistor to a maximum power converted in the resistor. We discussed in the theory last time, what do you think the answer should be? Yeah? What the value it should be? We discussed this in the theory. How much? Average power or the maximum power? When you give alternating supply, let's say the RMS value is RMS value 2 volt, okay? But you know the voltage will rise more than 2 volt, right? So if you use the RMS 2 volt, let's say the average power is 5 watts, okay? Average power is 5 watts, but sometimes you go maximum power, right? The maximum power can be how many times greater than the average power? Twice, right? Right? So now from the working you have to show. So I will show. In this case you should get half because average power over the peak power. Should get half. Final answer is half. Now you will get it. 3 marks. Do the working. So the average power over the peak power. So what are you going to put? Average power, what formula do you use? I naught, V naught. Okay, so we put I naught, V naught. Okay, the peak voltage, peak current, right? The average power, what do you put? I, what? I RMS, V RMS, right? Okay, so now what do you do? You convert to one type lah. Maybe the I naught, V naught, you change to I RMS if you want. Or you change the I RMS. Okay, I think I change the RMS value to peak. I RMS in terms of peak is what? I RMS change to peak is I naught root 2 V naught root 2 I naught V naught, right? So you got 2. Oh, over, sorry. So I naught over 2. I naught over root 2. So finally you get what? You get half, right? You should get half. Right? I naught over root 2, V naught over root 2. So yeah, so half, right? So average power divided by the peak power is half. Okay, makes sense, right? Okay, so remember this is quite important. Average power is half of the peak power. Okay. Okay, so that's one question. Go to another one. Okay. So next question. So alternating current, resistance, I changes this formula to the same formula. So what is frequency? 380, but 380 is equals to 2 pi f. You get your frequency. 380 is your omega, right? Then, oh, that's 2 mark. Then RMS current, just 9.9 divided by root 2. RMS current sense? Okay, then last question. Prevent overheating. The mean power dissipated in R must not exceed 400 watt. Calculate the minimum resistance of R. Okay, so you need to decide, you need to use the peak value or the RMS value. To prevent overheating, the mean power of the R must not exceed 400 watt. So this is your mean power. Calculate the minimum resistance of R to be used. So above the equation given is for what? Above is the current, current formula, 9.9 is the peak. Okay, the above the peak current is 9.9 ampere. So what formula do you use? Power equals to which formula is most suitable here? I squared R. You use I squared R. You want to find the R? I use which I? Peak current or the RMS current? Power use which power? Power use 400 watts. 400 watts is average power or peak power?
Average.
It's average power. So I use which I?
RMS.
RMS. You have to use RMS. So I squared R to be used because I and R. I must be RMS value. Okay. Use RMS value, get your resistance. Okay, so that should be the working, right? Yeah, the biggest problem in this topic is it RMS to be used or peak value to be used? Okay. If they say average, RMS. If they never say anything, still RMS. If they say only, when they say peak, then you use the peak value. Okay. Same question.
So that means if the question is now, if they say doesn't exceed, you don't say mean, they just say the doesn't exceed 400 watt.
Yeah.
Then use RMS.
RMS. Sometimes they ask, what is the? Sometimes they ask, what is the peak power generated, and what is the peak current normally? Peak power. Okay, so this question complete the figure showing the connection of the supply of the load to the diodes. Complete the circuit. So, come on, where do you attach the supply? Supply. Do you attach to the top, or do you attach the supply here to the side? Where do you think it's going to go? Supply you put on the top. If you put at the top, is it able to flow? Current flow. Is it top? Supply? Cannot be right. Have to be at the side. So supply should be at the side. Right? So if you connect to the side, current flows here, down, flows here. Right? So on the other way around, current comes here. Up. Yeah, the supply connection should be at the side, right? Yeah, those relays at the side, good. Yeah, cannot be top, cannot be top. Right? If you put top and bottom, the current flow up, is stuck. Yeah, can't go anywhere. Yeah, so the supply should be at the side. Yeah, so to connect two wires here and here. Yeah, load have to be on the top and the bottom. Yeah. Load have to be on the top. So be careful when each is at the side, which is at the top. Or another way, diode must come up and join back. The junction should be the load junction, right? So here, the diode is come out, join back. So these two should be the load junction. This is the load junction. Right? Collect the load. These two connect here. Right? Okay. So not always the top is always load. It can be the other way around. Okay, then P. Suggest for advantage to use the bridge rectifier rather than a single diode. So more power is available to the load. More power is available to the load. Full rectification. Okay, state what is meant by smoothing. Smoothing is preventing the voltage from decreasing to 0, right? But what is the term? Huh? Reduction in the variation output. Yeah, preventing the voltage from drop to 0, right? Yeah, reduction in the voltage drop. Smoothing. Reduction in the voltage drop. Okay, so we go to the last question. Last question is what? State the effect of value of capacitor, smoothing capacitor in relation to smoothing. So you know this, right? And greater C, because C is inversely proportional to the potential drop, so less potential drop. So capacitance produces more smoothing, yeah, for the same load. Product RC. So more capacitance produces a smoothing for the same load. What's the question? Only 1 mark. 2 marks. 2 marks. Either this for the same load. For the same load, the given. Okay. So capacitance, peak capacitance is small voltage drop for the same load. Should be for the same load. Okay. So more questions, just we glance through very fast. So again, another alternating current, 50 Hertz shown in the diagram. So first question, T1, use figure in 6.1 to state the time T1. Oh, so what is the value of T1? So it's the period, right? So you can find the period one. So its frequency is 50 Hertz, so 1 over 50, right? Oh, sorry, stuck. So 1.5 period, yeah. So find the period times 1.5. 1.5 period, right? So triggers 1.5 period. So T1 is 1.5 period. So find the period times 1.5. Okay, then peak value just read from the graph. So how much is that? 15 plus 17. 17 volt. So peak value is 17 volt. Just read off from the graph. So easy mark. Then the root mean square value, just the 17 over root 2. Get the mark. The mean voltage is 0. For sinusoidal, same area on top and bottom, mean is 0. So I think all like easy mark, if you know. Okay, last one, B. The series supply is connected in series with a resistor of 2.4 volt. Calculate the mean power. So what formula to use? On top just now they give V voltage graph. So what formula to use here? Power equals to V squared over R. You know the R, you know the V. So V squared over R. Which V you use? RMS of it. So give me RMS. So average power. So RMS. Okay. Same question. Sure. This one, right? We did this question. Oh, this is a different question. We haven't tried this all, This one, right? Okay, so yeah, another one question. So, say voltage, capacitor, resistance all shown, and value is not given. So they said this is the V versus T graph. So peak voltage just 4, right? Peak voltage is 4. Root mean square voltage just over root 2. The frequency shown, what is the frequency? Frequency just the peak to peak, find the period, then 1 over period is your frequency. Okay, easy mark. Then B, the capacitor is 5 microfarad, looks different. Capacitor is 5 microfarad, the single diode, the single discharge capacitor through R, okay. Determine the change in potential difference. Capacitance is 5 microfarad, find the change in potential difference. So how do you find the change in potential difference? This is different. Capacitance is 5 microfarad, okay. What is the change in potential difference? So C equals to Q over V. Changes of Q over changes of V is your capacitance. They're asking for changes of V. So C we know. So we need to know the charge, right? How much charge has been released? Can you find charge anywhere? Oh, we can't find charge here. You know the peak voltage, you can root mean square, get frequency. So change in voltage is determine the change in difference. The capacitor C as okay, from the graph now. From the graph we can get the change in capacity. So what is the change in voltage? 4 become, how much is this? 2.4. Yeah, 2.4. So 4 volt become 2.4. So 4 minus 2.4 is 1.6 volt now, right? Yeah, so first answer. So 1.6 volt. So yeah, so from the graph we get the changes in voltage because we don't know the charge release. Okay, so the B1 is just from the graph. 4 become 2.4. Okay, next, determine the change in charge on each plate of the capacitor. So this we use C equals to changes of Q over changes of B. So we find the changes of Q. Okay. So C equals to changes of Q over changes of V, your capacitance knowledge. So you find the charge. Okay. Okay. So then show that the average current is this. So how do you find the current? You know the charge. Then how do you find the current? Current is rate of flow of charge, right? I equals to Q over T. You know the charge. What time do you use? What time do you use? Oh, this is the average current. I use the period. Use the period. Okay. You get that?
Like the time it takes to drop.
During discharging, right? But this here the current is what? The current is it the average current? Show the average current. So the average current is the entire area, right? So they choose discharge time. Oh yeah, 7 milliseconds. But yeah, 7 milliseconds. Yeah, during the discharge time. So from the top to here, just during discharging, right? So changes of Q or changes of T, the T is the discharging time. So 0.7 milliseconds is the discharging time. Okay. Okay. So put it in mind. So the charge, we know the charge released by the capacitor. So the duration of charge release is the duration of the discharging. Okay, in the PowerPoint we did the same question, but the ripple is too small until it becomes like equal to period. Okay. So here the ripple is quite big, so we just take the discharging time. So from the peak to the drop here, that's the duration you take. Okay. Okay, then finally, value of current given to estimate the resistance of the resistor. So how do you find this? Value of current given in V3 to estimate the resistance of the resistor. So you know the average current. Okay. You know the average current, you find the resistance. How you can find the resistance? What else you know? You know the current, capacitor, frequency given, root mean square, peak value given. Do you know the voltage? Yeah, from the voltage now. From the voltage, V equals to IR. Which V do you use? V equals IR, right? Which V do you think suitable for this? RMS, right? V RMS equals to I squared. I is the average current. Okay. So V RMS. They estimate the resistance of the resistor. Yeah, V RMS. Average PD 3.2. Okay, the PD they use is this PD. You know the 2.4 average is how much? Average of this. So 4 plus 2.4 divided by 2 is 3.2, right? So they take this average voltage. This average voltage. Okay, because from 4 volt for a resistor, okay, you have a resistor. The voltage of the resistor, the voltage across the resistor is from 4 volt. It dropped to 2.4 volt. Okay, the average current is found to be the one given. Okay, so this is the average voltage. So this is 4 volt dropped to 2.4 volt during the discharging period. So the average. So to find the resistance, so V equals to IR. So average current, average voltage for this, for the discharging. For discharging. Okay, so forward, so it should be 3.2 volt to be used. Okay, during the discharging. Oh, this is slightly different for discharging. Okay. Okay, so yeah, so this continues. So you can see lots of questions here. So this one also slightly different. So bridge ABCD, label positive connection, load R, state which diode are connecting when terminal Y supply is positive. Terminal Y is positive, which diode is connected? So Y is positive means which is connected? CNA, right? CNA. So when Y is positive, sorry, not C. So current flows here, B and D, right? B and D. So this should be B and D. Okay. Next, full wave rectification. So use the determine the mean power dissipated in the resistor. So mean power is resistance given. So what else given? V given. So V given. So use what? V squared over R. V RMS over R. Right. So get the mean power. Then figure 6.1, draw a symbol for the capacitor connected, increase the mean power dissipated. So capacitor always connect parallel to the load. These all are standard questions, always comes up. Only towards the end, it becomes a little challenging. See, the capacitor is now removed from the circuit. The diode A stops functioning of different type. So the capacitor in P2 is now removed from the circuit. The diode A stops functioning. So that now has infinite resistance. So A got infinite. Draw a variation with time t, the new potential difference across the resistor R. So 2 minutes, come on, think about it. Remove the capacitor. The diode A is spoiled. Okay, we go back. So they want you to draw back this graph. Yeah. The capacitor removed, so no smoothing.
It's a capacitor you added parallel to the.
They added towards the end. The capacitor is now removed from the
But
B2 symbol capacitor connect to as increase the mean power. Draw a symbol of capacitor. Yeah, the part 2 it was connected. Where to connect? Yeah, parallel to the resistor. So you connect here. Always to the load, parallel to the load. Okay, now no capacitor, so the A is removed. A is spoiled, right? Diode A stop functioning. Okay. So how the graph going to look like? So A is spoiled. That means no connection. Yeah, like no connection there. No A. So no capacitor. So how the graph going to change? Big change. Big increase.
So the middle mountain is what?
So half wave rectification. Half wave. Current flow. One round, but the second round can't travel. Block. So half wave rectification. You get half wave rectification. Maybe the first one appears, the second one doesn't appear. Half wave rectification. Period and same peak values. Okay. Okay, so continue to do your questions for the previous topics. Do the topical, do the exam made. Okay. For every topic, the previous topic too. Okay. So next class tomorrow, C7 homework. Okay. And what the third one, right? D3, right? We're just going to spend about 40-45 minutes for these two. And another 1 hour we're going to use for theory type. You continue with the quantum physics next class. Okay, 1 hour into that. Yeah. 1 hour going to be your experiment design. 1 hour we go back to theory. Quantum physics.
Go.
Quantum physics. No. Yeah. Altogether 15 topics. So this is the 11th, right? So you got 4. There are 4 to go. So I'll finish by like 1 week before your trial. Quantum physics is modern physics, whatever discovered by Einstein. So it will be very theoretical.